Hello all, myself Dr. N. Komagan Prabhu, Associate Professor from Department of Oral and Maxillofacial Surgery, would like to give you an insight on the topic local anesthesia and neuroanatomy and the neurophysiology. This topic will be very useful for beginners. So coming to the basic introduction of the neuroanatomy and neurophysiology, you need to know the basic understanding of the structural anatomy of a neuron and also basic conduction mechanism of the sensory and motor nerve. So this will pave way for better understanding of the mechanism of action of LA. So before we go with the anatomy, you should know about the neuron. Neurons are basic structural unit of the nervous system. The central nervous system comprises of hundreds and billions of neurons. The signals are basically transmitted via synaptic presence on the dendrites and cell body, which are the integral part of a neuron. The signals they always travel in unidirectional flow. From an axon, the signals get carried to the dendrites and to the cell membrane of the subsequent neurons. There are different kinds of neurons. They have the sensory, which is also called as the afferent. The other one is going to be motor or efferents. The sensory, they basically transmit the sensation of pain from the peripheral process to the central nervous system. Then from the motor being, it conducts impulses from the central nervous system to the periphery. The different kinds of neurons, they interlink by interneurons. Now coming to the basic parts of the neuron, which we already discussed. The cell body is the main integral metabolic structures inside the neuron. Then you have the long cylindrical cable-like structure called as the axons. Then the cell body and the dendrites. And then there are the synaptic junctions which are formed between the neurons. They basically block weak impulses and allows only the strong signals to pass through. There are different types of synapses, chemical synapses and electrical synapses. The chemical synapses are basically mediated by neurotransmitters like acetylcholine, norepinephrine, epinephrine, histamines, GABA, and glycine serotonin. Electrical synapses are basically transmitted by electrical currents. Okay, so they basically conducted within a protein tubular structures called gap junctions. Okay, a nerve fiber always comprises a long cylindrical structure like a cytoplasm, which is covered by a thin sheet called axonema. This is there is a gelatinous substance, that is the axoplasm, which is separated from extracellular fluids by a continuous nerve membrane. The membrane is covered by a lipid-rich layer called myelin sheet. Okay, so this is the basic anatomy of the axons. It comprises of a long cylindrical structure with myelinated portion and unmyelinated portion. Okay, so each myelin sheet is basically having a Schwann cells and also a cell nucleus within its structure. The myelinated nerves are wrapped around by an insulating lipid layer called myelin, and as I told you, it contains Schwann cells. Constrictions at the intermediate portions, which are not covered by the myelin sheets, are called nodes of Ranvier. Okay, now when you take the cross section of the cell membrane, they are made up of a bilipid phospholayer, and it is permeable to certain molecules via specialized pores or channels. Okay, these channels allow certain electrolytes like sodium, potassium, and calcium alone. So before we move on, so you should know the terminologies of a fasciculi. What is an endoneurium, a perineurium, epineurium, and an epineurial sheath. The endoneurium being it covers each individual nerve fiber. A fascicle are nothing but bundles of 500 to 1000 nerve fibers put together forms a fasciculi. Perineurium is each individual fascicle is covered by a layer called perineurium, and epineurium is nothing but it's a alveolar connective tissue supporting the fasciculi, and these are supplied by rich nutrient vessels. An entire structures of all these structures will be covered by an epineural sheath, which is the outer layer of an epineurium. So simply for better understanding, the entire cross section of the peripheral nerve fiber can be compared to a pomegranate fruit. So the individual lobulated part of your fruit is considered to be your neuron, which is covered by a layer of endoneurium, as you can see in the histological slide. And other put together, the entire group of the individual lobule is nothing but it's called as the fasciculi. and each fascicula is again covered by a layer called as the perineurium, and the entire bundle of the particle fruit is compared to a structure called as the epineurial sheath. For better understanding, if you could put the entire fruits into one nerve bundle, this is how it will look. Okay, the outermost thick layer forms the epineurial sheath, and the innermost layer, which is contained each fruit, is covered by a layer called as the endoneurium, which is the final place for your local anesthesia has to penetrate for better action. And then there is an intermediate section, which is also again covered, put together the entire fasciculi, which is again covered by a layer called as the perineurium. And so always remember, the thicker the perineurium, the slower the rate of the local anesthesia diffusion. The innermost layer of the perineum is the perilemma, which is the main barrier to diffusion. Now, what are mantle and core bundles? Fasciculi which are closer to the surface of the nerve are called mantle bundles, and the innermost core fasciculi which are inside the nerve area is called as the core bundles. Okay, first initially when the local anesthesia is given, the mantle bundles gets anesthetized. Okay, whereas the core bundles are lately contacted by the local anesthesia. So because of the increased barrier to solution and its location is the farthest distance, it takes some time for the anesthesia to take over. So nerve carries messages from one part of the body to the other. These messages of the electrical potential called impulses. As I already told you, these are initiated by the chemical, thermal, mechanical or electrical stimuli. For nerve to get activated, action potential has to be generated by a process called depolarization. Okay. So for basic, coming to the basic electrophysiology of the nerve conduction, these are the various stages: the resting state, depolarization phase, repolarization phase. For example, a resting phase of a nerve is a charge which is minus 70 millivolt present along the nerve membrane. It's in first initially it is in the negative electrical resting potential. Okay, the interior of the nerve is always negatively charged compared to the exterior. Okay, the nerve membrane is freely permeable to the potassium ions and is retained by electrostatic attraction within the nerve. It's also freely permeable to the chloride ion, but always it remains outside the nerve membrane. Since the sodium ions are positive charged electrolytes, they are getting attracted to the negative intercellular protein. But during the resting potential, it does not easily go inside because of the gates which are present along the pores, which doesn't allow the sodium ions to gain entry. When an action potential is generated, okay, or the nerve getting excited, okay, what it happens is there is a depolarization phase. From a slow depolarization, the firing will happen, and rapid depolarization happens at a charge of plus 40 millivolt. Okay, this is the picture in which this depicts where the sodium gate which tries to open and the sodium ions gain entry inside the nerve axoplasm. Okay, so from minus 70 millivolt, it gains to a charge of plus 30. It goes beyond the threshold level. So next, after this, once the conduction has taken place, the action potential is terminated by the inactivation of the increased permeability to the sodium. The permeability to the potassium also increases and massive efflux happens. So then back to the previous stage of resting state follows. Okay, so the innermost gate of the sodium channel here closes and doesn't allow the sodium ions to gain entry. And there is a massive influx again of potassium ions back to the axoplasm of the nerve. So you should all know what is the sodium potassium pump mechanism. After the repolarization phase, when nerve comes to a resting phase, there is a slight excess of sodium which is present within the nerve cell. Okay, and an excess of potassium ion is again present in the external. So initially the sodium has to be expelled out and potassium ion again has to be driven back inside. So this brief period is called as the refractory period for the nerve to again for it to help to conduct another impulse. The energy for the metabolic activity of the entire process comes from ATP, adenosine triphosphate. Entire time consumed for an impulse propagation is 1 millisecond. The depolarization is 0.3 millisecond. The repolarization phase is 0.7 millisecond. So a refractory period always exists for another impulse to get generated, often equal or above, more than that. Okay, so the most important is the spread of impulses. Remember, a myelinated nerve fiber with synaptic junction and containing a node of Rano allows saltatory conduction. That is why it allows faster conduction of nerve impulses. So a myelinated nerve has to expose almost to 8 to 10 millimeter of nerve must be covered by the local anesthesia solution for an effective blockade in conduction process. Okay, now when you classify the peripheral nerve fiber, they can be classified as A delta, A beta, and also B fibers and C fibers. For acute pain, okay, that's basically the A delta fibers are the most common entity, and C fibers for the chronic pain. Even touch proprioception mechanisms are also being carried out with the individual fibers. Some may be more, some may be minimal. Okay, so with this, I have concluded my discussion on neuroanatomy and neurophysiology. Thank you.